All right, yeah. I think Shao should be recording. Shao, did you start recording? Uh, cool, great. Okay, let us start. Okay, so the first half of the lesson, just a really quick recap, was talking about basically what functions are, and then what is wrong with my screen? Okay, yeah. So the first half was talking about basically what functions are and how you define them and the domain and range. And the next thing we're going to talk about is a special type of function called the inverse function. All right, so let's first of all talk about what inverses are. We first learned that functions, let me make this right color. So we learned that fx, an example of function, the simplest function is fx equals to x, or fx equals to x plus 2. Now, what does this mean? To think about function, to understand inverse functions, you have to think about functions as a output machine. You have to think about it as a machine, right? Like this. You put in SpongeBob into the machine and it outputs Patrick. You put in a hamburger, it'll output Moosey. So basically, given any number, it should output some other number that comes out of it, right? So in this case, fx equals to x plus 12. And if you're taking 2, it will add 12 to that number and then make it 14. And if it's 13, it will add 12 to that number, make it 25, right? So if, like for this one, you would have an input machine, which is x plus 12. And if you're given any number x that you put in, it should give you x plus 12. This is important because now a function is a mapping from an x to a y, right? It's a mapping from the set x to the set y. And the value of x should be mapped to a value of y. Like here, every x should be mapped to x plus 12. And a very valid question we can now ask is that if we know, what if we're given 25 and we want to find 13, right? What if we want to go backwards? Because obviously this input machine can be reverse engineered to work the other way. If we take Patrick, what if we want to take Patrick and create SpongeBob? Uh, this is possible in math because there are no limitations to what we can do in math. So we can definitely get back SpongeBob. Yes. It's just on my desktop. Yep. So that's what we need inverses to figure out how to go from the Patrick to the SpongeBob, how to go from the outputted number back to the regular inputted number, right? So the inverse of a function is f of negative 1, right? And the function is inverse of the property that if fa equals to b, then f negative 1 b equals to a. Right? So think about this again as our input machine. If we're given A, we're going to, this is called F, our machine is called F, then we're going to output B. And if we're given B, we need to find some sort of machine, F negative 1, that will give us A. Right? So let's do the simplest example of a possible inverse function, which is if fx equals to x plus 12, what would our inverse be? Does anybody know? Really quickly? X minus 12, perfect, yeah, because what you do is that you want to take x plus 12 and get back x. So if you do x minus 12, you can get back what you had before, which is you get back x, right? So here, if we look at this, if x2 equals to 14, f negative 1 14 equals to 2, right? We want to get back the original number that we started with. And it's important because we want to, again, reverse engineer the machine. The inverse of a function is the same points as the original function, except the x and the y's are reversed. If you learned graphing before, an inverse function is actually a reflection on x equals to y. Because to get the same graph back again, you have to flip every single AB, right? AB point becomes BA. So if you take this point and you flip it, it becomes this point. So every point is actually flipped or along the axis of x equals to y. And that's the gist of how a basic inverse function works, right? And now we know how an inverse function works and how to use it. Now let's look at one of the most important inverse function methods, which is this. This is so useful that almost every single inverse function question is template using this equation. And what this means is that if you think about it, let's say fx, if you have a function fx, if you take x and you put it through a machine called f, and then you put it through a machine called f negative 1, what are you going to get? You're going to get x back. Because if you put x through, you get fx. And when you put fx, this converts it back to its original form, which is just x, right? And the same thing works if you take f negative 1 and then f. A disclaimer, f negative 1, x, does not mean fx to the negative 1. These are completely different things. The notation f negative 1 is special to functions, where f negative 1 denotes the inverse, and f x to the negative 1 denotes nothing. Well, it does denote something. It just doesn't denote anything based on f negative 1. It just denotes that it's just to the power of negative 1. It has nothing to do with inverse functions, right? So this is the fundamental theorem of inverse functions, that if you take a number, you take a value, you f it, which means that you put it inside the machine and you revert it back, you're going to get your original number. Is that clear? Yeah, imagine you use a hamburger. Yeah, you can move to trade your own hamburger, right? Like if you have $3 and I pay Xiao $3 for a hamburger, I can now give the hamburger back to Xiao, assuming the price of the hamburger hasn't changed, and he's going to give me back $3. It's like trading. It's like trading. Assuming the values don't work. The values don't change. Yeah. So yeah, it's a really great example. Think of it as trading. So let's look at this one. Determine the inverse function of fx equals to x squared plus 3x plus 1. Give you a few seconds to figure that out and put it in the chat. And we'll take up the answer. We have some answers in the chat. All right, so do we have any answers in the chat? X minus 2 times x minus 1. That's close, but the actual way is a bit more complicated. We're gonna talk about a simpler version first. If you don't have any ideas, here's a hint. So if you find, all right, the hint is here. The hint is actually here. To draw an inverse, all you need to do is swap the x and y coordinates of each point. That's your hint, right? So let's say you're given something like, let's do a simple one. Let's say x equals to 2x plus 3. How do we find the inverse of this equation, right? So what we would do is that we would actually take fx like this, and we would do y equals to 2x plus 3. Think about it, this is y equals 2x plus 3 because it's the same thing if you graph it. And then you're going to swap the x and y coordinates. So x equals to 2y plus 3. And then what you're going to realize is that if we simplify, we have y equals to x minus 3 over 2. That's how you would do it if it was one digit. Basically, you use the hint here that you swap the x and coordinates, y coordinates for each point. You first of all, you write out the corresponding equation to the function. You're going to swap the x and y coordinates of every point, and you're going to solve for the value of the answer. All right. So we'll give you 1 more minute to figure out the inverse of this equation. Oh, it doesn't matter. There isn't even a solution written to this question. Yeah. Isolate y, sorry, x. Yes, exactly. Elaine is very smart. Or is. All right. I don't. Are there any other? Does the answer have square roots? Yes, there are square roots. No, you. Yes, there are square roots, and it hint is it's not. There's more than one solution. That's a hint. Also, we can go through. Wait. Right. Wait. Is the answer of square roots -3 plus square root of 5 over 2? That is very, very close. Very, very close. So that might even be it. So let's look at how we start this, and then we'll quickly finish it off later in a second. For those of you that are maybe stuck, here's a start to the problem. Maybe you can finish it. So you would first of all, again, write down the start to the equation. So y equals to x squared plus 3x plus 1. And then you would see that x equals to y squared plus 3y plus 1, right? And then what you realize is that I want to isolate the y, because here I want to write y equals to something x. I want to write y equals something x. And the hint for this next part is that I want y to be on one side, right? I want all the y's to be on one side. So what I could, because x is treated technically as a value that we know. We pretend that we know x because we want f negative 1x. So we pretend that we know x, right? So x here is treated as a constant. So you probably learned even in elementary school that you move all the constants to one side and all the variables to one side. So let's try that. Y squared plus 3y equals to x negative x plus 1. And here we'll give you 30 more seconds to try to figure it out. So here, if you don't actually know, this is actually a a way to solve this problem by completing the square. So if you don't know what completing the square is, I just realized some of you might not know what completing the square is. What that means is that if we're solving a quadratic equation like x squared plus 2x plus 1, or plus 2, or just something like this. One way you can do it is that you can definitely just do x plus 1 times x plus 1. But there's another way you can do it, is that you can actually write this as x plus 1 squared equals 0. And this is called completing the square. You're changing a quadratic equation into a square of a number plus a constant, right? So you're expressing this in some square number plus some constant. And that's what completing the square is. So how is that useful here? How is that hint useful here? Well, to solve this, what we can do is that we can actually write this as y squared plus 3y plus 3 over 2 squared. And we can write the right side as negative x plus 1 plus 3 over 2 squared. We're basically adding 3 over 2 squared to both sides. And you might not see why this is important, and that's completely fine. But you can see that from the next step that this is almost essential, because what we can do now is that this actually now completes the square. What we want is to complete the square on the left side so that the right side can, we can treat this as a variable. Again, x is a variable, so we treat this as a variable. So y plus 3 over 2 squared. If you want me to explain this a bit further about how to complete the square or how to calculate these squares, I can do that as well. Equals to this negative x plus, we'll just 9 over 4. 9 plus 4 equals to 13 over 4, something like that. And then y plus 3 over 2. Remember, because we're square rooting both sides, so it's equal to plus minus negative x plus 13 over 4. And then here, the final step is y equals to root, yes. What am I doing? Because you're square rooting a number, so you get like plus minus square root negative x plus 13 over 4. And then the final answer will just be y equals to plus minus root negative x plus 13 over 4. And then subtract 3 over 2. If you want to check this, you can. I think this is probably right. I think it is right, yes. So if it's not, you can say in the chat or object now, and I'll check. But otherwise, what this method is basically, it's kind of more confusing than adjustive functions, which is why some problems actually use different solutions from other types of problems, where this one you had to complete the square, right? And once you complete the square, you figure out that there are actually two solutions to the equation. But how you figure that out is that for your first thought process is, well, let me just do it the regular way, right? Swap the x and y coordinates. Then you realize that I want to complete the square, otherwise I can't isolate y, right? If I isolate y here, I get nothing. So I have to complete the square, add this to both sides, complete the square, and then I figure out the answer here. Right? So that's how you would do a kind of harder inverse function application, where you have to use both finding inverse function and advanced algebra, aka completing the square. Are there any questions? If there are any questions, feel free to ask and I will explain. If not, we will continue. All right. So the next question that is probably normal to ask of anything is, do all inverses have functions? Oh my God, have inverses that are functions, right? So what does that mean? That means that are all inverses of functions also functions? And the answer is no, right? Not all function inverses are all functions. They may exist, but they're not functions, right? Because existing just means that it's a relation. And yes, all relations have inverses, but not all of them are functions, because we usually care about functions more because, like we said, a function is a map from one x to one y. One x can only map to one y. And that's why we care about functions. And that's why we care about inverse functions also being functions, right? So how do we check if a function is an inverse function? Well, we use almost the same thing as the vertical line test, except this time we do the horizontal line test. And the horizontal line test tells you if the input is the inverse of a function. Now, how does this even make sense in any way? How can this possibly make sense? Because if you think about it, let's say this is a function. The vertical line test tells you it's a function. If you take the inverse, it's going to be reflected along x. So it's going to look something like this somehow. And if you take it, it's not going to be a function, because think about it. An in horizontal line test is checking if one y has two x's. Isn't that the same thing as checking if the original function, or let's say this is the original function passes the vertical line test? Because these two are the same thing, except they're just rotated along xy. And one way you can actually or intuitively memorize the horizontal line test is you can realize that the horizontal line test is just the vertical line test flipped on x equals to y, just like every other point on the graph. And we talked about how every point on the graph is a reflection on x equals to y. So wouldn't the horizontal line test also just be a reflection on x equals to y? Right? If I reflect this, it would be that. If I reflect this point, it would be this point. Right? Isn't that a similar way to think about it? So that's how you would figure out, right, using the horizontal line test, which is just a flip version of the vertical line test, just like a flip point is an inverse of that point. Does that make sense? Otherwise, if you don't want to memorize that way, you can just remember HLT and VLT. That's great too. So let's look at this one. Another question that is, I think, also made by Xiao. By the way, we've basically covered everything there is to cover about basic functions now, and then we'll move on to a few problems that we'll see later as well. This one is a kind of a as I was saying, this is a AMC 12B problem, which looks intimidating, but it shouldn't be that bad. Yeah, this one could be a thinking question, which also brings me to a point where thinking questions are kind of just contest questions, right? If you understand contest questions, it's pretty easy as well to relate that to contest questions, because contest questions are just harder thinking questions. All right. So let's look at the question and then see how we could possibly solve it. Right. Right. So I'm sounding like Albert now. Oh no. If fx equals to ax plus b and f negative 1x equals to bx plus a, and a and b real, what is the value of a plus b? I don't even think I've done this one. I'm just going to see how this works. So let's first look at what we have, right? Let's analyze this question. We have fx equals to ax plus b. All right. And we also have f negative 1x equals to bx plus a. Which means that if you give me an x, I can give you an ax plus b. And if you give me an f negative 1x, I can get back bx plus a. And I want the value ax plus b. Let's look at one way we would possibly do this, and then we'll think about another way that we could do it, right? So there's a way that I'm thinking of. So the first way that I would do this, yeah, I am live solving because this is Xiao's question. All right. So the first way I would probably do this is I would see that fx equals to ax plus b. So let's find the inverse of fx, right? Because we know the inverse, so let's actually find it. I want to make sure that this inverse is correct, right? So what that is that basically we have y equals to ax plus b, and then we have x equals to ay plus b, ay equals to x minus b, and then we have y equals to x minus b over a. I think this is right. Yes, x minus b over a. And then we see that this is also equal to bx plus a. So we have that. And let's see what we can do with this, right? Because we understand that this is actually f negative 1. That's why we can actually plug in bx plus a, because we already know that this is the inverse function. Solving, we have x minus b equals to abx plus a squared. So I think we have because the coefficients here should match up. I think AB equals to 1. I might be wrong though. I just want to try it out. AB equals to 1, and then negative B equals to A squared, I think. All right, so then what you would do now is that you would plug in negative B here. So negative A cubed equals to 1, right? If I plug in negative B equals to A squared, I would get negative A cubed, yep. And then equals to 1 actually, because here I would get B equals to negative A squared. And then I would get A equals to negative 1. If I plug it in, I get B equals to negative 1, and then A plus B equals to negative 2. Is that the right answer, Xiao? Okay, great. Let me see. Why is y equals to x minus b over a equals to bx plus a? All right. So that's the key observation we can see in the question. The key observation we can make is that we first want to find f negative 1x. How do we find f negative 1x? We found that it was equal to x minus b over a. You get that part? First of all, we know fx, and we tried to find f negative 1x. Does that make sense? Yes, good. Okay, so notice that they also gave us an extra piece of information that f negative 1x is also equal to bx plus a. Let's say that it's kind of like 1 apple equals to $3, or let's say 3 Canadian dollars, but it's also equal to 26 Chinese dollars or something like that, right? And then what you can do is, since you know the price of that, 3 Canadian dollars equals the 26 Chinese dollars, you now know the conversion rate between Chinese dollars and Canadian dollars. It's kind of like that. Or you have something that bridges the gap between both of them. Yeah. So A equals to B and A equals C, so B equals to C. Exactly, precisely. They give you find out x minus 1 x by yourself, and then they give it to you again. So like Chinese yuan and then Canadian dollars, and then you equal them, you find the conversion rate. You get it now? Yeah, you're right. Great. Okay. Any other questions? Basically, once I found this, I equate the two equations. I find the 2 equations, and then what I do is I plug one of them into the other, because that's usually what happens, and then I get the answer of A and B, and then I find the answer. All right. So I'm gonna talk about one more really quick method just to sketch. I'm not gonna find the entire method. This is actually how I originally would have done the problem, but I didn't show this because I wanted to first show the slow method and then the efficient or / faster method. And the faster method you can do this is that there is actually an equation a few slides ago that I deliberately didn't talk about because I don't know how many of you actually remember this, but a few slides ago we talked about, where is that? It's hiding somewhere. It's hiding somewhere. Let me find it. It is hiding somewhere. Oh no, it's actually behind here. Yeah, it's behind. All right. So it's, oh my God, where is it? Okay, give me 1 second. This is technical difficulties. All right. There was I literally don't know where it is. Oh, it's later. Right. Okay, yeah, see that, there it was. All right. So f negative 1 fx equals to x, right? That's the main part of how you can do it. So what you can do now is that you have f negative 1x equal to x. And remember I talked about, this is the fundamental equation of solving any problem. Almost any problem can be solved with this method. It is literally the fundamental equation of inverse problems. And the reason for that is because any problem deteriorates into knowing fx and finding f negative 1x, or knowing f negative 1x or finding fx, or in this case, knowing both and trying to find out what the variables are. But still, you're given some information about f and some information about f negative 1x, and you're trying to equate the two together. And this is the perfect equation to do that, because you know the composition between f and f negative 1. This is called function composition. We're going to learn about this actually next week. But all you have to know is that this basically means that I'm taking f and I'm taking 2 inputs in a row, just like how I did. Remember, we talked about this. We have f, we put it into f negative 1, and we get back x. That's all you have to this is all the equation means. That's all the equation means. It's not too complicated to understand. And now using this, we're going to make something happen with this. I'm pretty sure this is a valid solution because I thought about it at the start, but we're going to keep working and see if we can actually do something cool with this. So f negative 1x is bx plus a, right? We plug it in directly, equals to x. Remember, functions can be plugged in directly, even if it's an inverse, even if it's any function. Inverse function is still a function, it's just denoted as an inverse. And also any function can be denoted as an inverse. So the function that's denoted as an inverse is just up to perspective, just like relativity. And then I don't know why I said be just like relativity. I'm looking too much into random stuff these days. All right, so that equals to x. No, it's ax was b. What am I doing? Ax was b. Ax plus b. All right. And then we have abx plus a squared plus b equals to x. Same equations as last time, as b equals to x. Same as last time, we can equate the two values, like the two coefficients. So ab equals to 1 again, and then a squared plus b equals to 0, plus b equals 0. And this again brings us to our same method as before. We plug one of them into the other, and we get a plus b equals negative 2. Any questions? Now this is way easier than the first one because we use the property. And when we use a property that makes the problem simpler, it will really make the problem easier to understand and also make it more efficient. This is also why you don't jump into a problem at the start, because if you just jumped in, you were like, oh, look, I'm going to use what I learned about inverses and just swap the x and y and write 3 pages of steps just like Nathan. But what actually happens is that it doesn't always work out perfectly as you want. 15 minutes left. All right. Yeah, now you can do MC12. Yay. All right. So we have just one more question, and then we're all good. Actually, one more set of questions. Really quickly, you're just gonna look at one question. Every question should be, how much time do we have? 5 minutes for each question. Perfect. All right, so the first question is fx equals to negative x minus 5. This question. All right, so we find f negative 1, 7 in 2 ways. This, I'm gonna just take it out because we already talked about this. To solve any inverse question, now you know 2 ways to solve any inverse question, which is really perfect in your arsenal. First of all, you have swap. You can do this on your own. I would really recommend doing this on your own because it's really great practice. First of all, it would be swap x and y. We talked about this, right? We talked about when we do y equals to ax plus b, we can swap y and x equals to ay plus b, and then find out what y is in terms of x, and that would be your x negative 1. Right, swap the x and y, and then find f negative 1, and that's going to be your answer. And the other way we talked about how we can do it is if we just do y is this text, I have no idea why, 2, this is going to be f negative 1, x equals x. Right, that's really cool way to do it. Second question is, how do we make fx equals x squared have an inverse? And the way we can actually do that is actually really cool. It's called restricting the domain. And this is actually something that you'll learn in later courses, which means I don't want to cover it too much. And it's not very useful unless you're going for harder math or just regular curriculum math. But how you make fx equal x squared have an inverse is that you restrict the domain. So think about something like this. Or not even have an inverse, just exist. Let's say I want this to be a function. First of all, or this, I want this to be a function. Is this a function? Well, no, because it doesn't pass vertical line test. How do I make it pass vertical line test? Well, I do this. I delete half of the graph that's here. If I delete half the graph that's here, now this passes the vertical line test. So it is a function. Now this is a function, but if I did this, this is not a function. All right, so remember this is called restricting the domain. I'm just gonna do short form, restricting domain. And you can make any graph have an inverse by restricting the domain to an interval. Even if I have something like this, or like even like this, This graph does not seem to have, this graph is definitely not have an inverse, but if I cut it from here to here, notice that now this part of the graph has an inverse, which is what I want. I want one part of the graph to have an inverse, so if I just cut it at one part like this, now this graph has an inverse. So any graph can have an inverse or exist as a function if I cut it at a certain interval. And you'll learn about intervals later as well. They will be explained, I think Elaine explained them as well, about how you can restrict the domain and about how like x equals to r, x greater equal to 3, that would be an interval, but intervals can also contain in like a short range, like from 4 to 9, and that's how you would restrict the domain either at an interval or split the function at a certain point and restrict the domain like this or restrict the domain like this. Those are the two ways you can restrict the domain. If you have any questions, feel free to ask. We still have ample time to finish the last question. So just quick recap again. For this one, you would either swap xy, just like the previous question, swap it, or fx negative 1 equals x. For this question, you restrict the domain either to an interval or to a certain portion of the graph and cut it off at a certain point. Now this last question, I'm going to give you 1 minute to do, which is what rational functions have an inverse, and in other words, what a, b, c, d are there where fx equals to ax plus b over cx plus d have an inverse. I want you to try this because this combines what we learned before and a thinking portion of it. And this is a common thinking question that you might get. So I would recommend trying to figure this out. Right. And also, if you have any other questions about anything we learned today, feel free to ask. Hopefully I'm not talking to myself. All right. Right. So now you should be familiar with finding any function and any inverse without too much of a problem, right? Inverse problems really can't get that hard with it. I really don't understand the question on the previous slides. Okay, Steven, which slide are you talking about? Once I finish this, I can go back. The previous one. So like the question where we had to find fx equal ax plus b. All right, okay. Steven, can we do this? I'll finish this question and then I'll go back. Is that okay? Yes? Okay. Well, thanks. I'll take that as a sure. Take that as a sure. Once we finish this, we'll go back to the previous slide and I'll explain it again. I just want to get through every single question first. If you have any questions about these ones, you can ask as well because I'm on this page already. If it's a previous question page, I'll go back to it after we're done this page because then I can remove all annotations and stuff. All right. So let's look at this question. What rational functions have an inverse, right? So again, we use almost the same method. I actually like the swap xy case if I can, because the f negative 1 case is you have to match the coefficients, which I wouldn't do unless it's a trick. Like it's just not as systematic as the first one. But if you like whichever method, you can use any one. It's kind of like whichever method you use a factor. It literally doesn't matter. As long as you can find the inverse, as long as you can factor, you can use any possible method you want. Just have to get the right answer. So I'm just going to write it out for you. I was actually doing this. So you actually get that f negative 1x equals to nice change of background, Lane. Equals to b, wait, dx b minus, oh wait, no, what am I doing? Dx minus b over cx minus a. You can try this by yourself if you want. It's literally the same process. In this one, it's actually easier because if you let y equals to, if you let x equals to ay, y plus b over cy plus d, this is actually easier than the one we did before because there's no completing the square. You move this thing to the right side, and then you move all the y's to one side. So you had y times something equals to something, and you have y equals to something of a something. This shows you that the inverse of a rational function is an inverse. right? So the inverse of a rational function is always an inverse because, again, you can do this. Intuitive and kind of harder to understand, which means I want to spend more time on it. This first part is just systematically. You find y equals x, you swap the xy, and then you find out what y equals how much x by moving it to the right, moving all the y's to one side, dividing, and then you get another rational. Should be easy to even, if you're more advanced, you should try to tell what kind of functions have inverse and what are they, right? Like if you see a rational function and like, okay, the inverse of this is definitely irrational. And I don't even need to do it to know it's irrational. And so if you don't, it's completely fine. You can write it out. It doesn't take as long at all. Now the next part actually requires a bit of intuition. And usually all thinking questions require some sort of intuition. And the intuition for this is that I need the original function to exist. Right? I need the original function to exist. I need both functions actually to exist. Right? I need both functions to exist. And what that means is that I have to have this to hold. Same thing. I always go back to the same thing because it's just one, right? It's just, I take f and I take f negative 1 and I get back x. It's the same equation for almost every single question. At this point, every time you see an inverse question, you should just close your eyes and just put it in because that's probably what it's going to be, right? And what you do is that you say that f negative 1x, you're going to plug it in, and you get a d minus bc over AD minus BCX equals x. And you realize that this thing has to equal 1. Now, when does this thing equal 1? A lot of people are going to say everywhere. And if you say that, you're going to lose all the marks that you got. If you did this and you did everything up to here, if you say A, B, C, D can be everything, you literally lose all the marks you took to get to this step. Because what your teacher's looking for is that they're looking for, can you understand that this cannot be 0? Because if you don't see this, everything you did here is almost completely useless. All right, 5-minute warning. All right, so this means that this equals 1, so AD minus BC not equal to 0, and that's your answer, right? Because AD minus BC can't be 0. What is, oh, wait, let me see. When did he give me the 5-minute warning? 27. All right, so I still have, 3-minute warning. Damn it. All right, I'll go back to the last question now.
You can go a bit over if you want. You can go a bit
Okay,
over. It's not a big deal.
I just need like 2 minutes over because
Yeah,
I was gonna
go
finish,
for
but
it.
then someone has a question, so I'm just gonna
No,
explain
no, no,
that.
no. Go for it.
All right,
Answer any questions. We can go a bit over.
cool,
It's fine.
cool. All right.
So you know.
So for this question, basically what you do is that you first of all, you find the inverse regular way. And then what you do is that you use this trick, this intuition that you have fx negative 1x equals x. You should always try that because you should know that these two have to exist. And to exist, this equation has to hold because it's the fundamental equation of inverses. And then since this has a hold, you get that this, you plug it in and you get AD minus BC over AD minus BCX, and that equals to 1. You see that the only reason this can hold is if AD minus BC is not 0. And this is the most important step because otherwise, if you don't see that and you say that anywhere can happen because these two cancel out, then you forgot the fundamental step, which means you probably won't get any marks even if you did all of this. And that's why you shouldn't rush your questions. You should plan through your work. You should see that this can't be 0 because 0 over 0 is indeterminate form. So you get AD minus BC cannot be 0, and that will be your answer. All right. So this is, how did you get AD over BC? You just plug in this into F. So what you would actually get is that you would get F of dx minus b over cx minus a. And then you would get like something really crazy. Like you would get a dx over b minus cx over a minus b over c dx minus b over cx minus a plus d. Like you would get something pretty confusing, but the good thing about it is that if you simplify everything, it comes down to this. You just have to simplify. This is why it's kind of a harder question, because it's the intuition is kind of, yeah, you see. All right. So it's kind of, the intuition is harder to understand, but it's just simplification, 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 because it has to simplify. If it doesn't simplify, you literally have no other way to do it. All right. So I will, yeah, that's fine. Okay. So the last thing we're going to do is we're just going to spend one more minute, and then we're going to take out that last question. This, even if you're grade 9, the intuition should be, you should have enough intuition to understand it. And if you don't, it's fine for now, because this is grade 11 stuff. But the good thing about this is that even if you're grade 9, you can kind of understand the thought process behind it, because it's just a few equations, it's just a few concepts like functions, fundamental equation of inverses, what an inverse is, vertical line test, horizontal line test. Once you get those in your head, you should be better and better at solving these kind of questions, because you see what concepts you use, what concepts there are, what equations you have to use, and how to plug them in the strategic way to get your answer. Yeah. All right, so last one, I'm going to quickly talk about this. Hopefully and if there are any more questions, feel free to ask and I'll go back. But for this one, the intuition again is that you see the fundamental equation as f negative 1, fx equals to x, right? So then you have x of bx plus a equals to x. So then you have a, bx plus a plus b equals to x. Again, you just plug everything in, and then you get that abx plus a squared plus b equals to x, right? Remember, we talked about a function which we can represent this as this. And then what f of bx plus a is, it's f of this x. This x becomes bx plus a. Think of this as the old x, right? But now this old x becomes bx plus a because it's function composition. Right. We're gonna talk about more about function composition next week. Don't worry, we'll cover this in a lot of detail if you don't understand. But basically, what bx plus a is that you take this x and you plug in what you have here. So what that means that like fa would also be equal to a squared plus b, something like that. And then you get this, and then you find out that ab equals to 1, and a squared plus b equals to 0, and then you get your answer.
Hey guys.
Hello. Hello.
You
All
almost
right. Yeah, I just finished explaining.
Cool.
Why is a squared plus minus b equals 0? ab plus x equal b plus equal, because this is x plus 0, right? The coefficients have to match, so this has to equal to this, which is 1. And then this has to equal to this, right? Because I can't have any other way for these to be equal to each other unless the coefficients all match. Does that make more sense? Yeah. Do you get it now? Great. Okay. So one more time, f negative 1x, you find the fundamental equation, you plug it in. This x now becomes your new x that you plug in, right? This bx plus a now becomes your new x that you plug into your new equation. You get this, and then the coefficients have to equate. Otherwise, the equations can't be equal. They have to be equal, so the x's have to match, right? Otherwise, how can they be 0? So since the equations match, you have a system of equations that you can now solve to get your answer. Great. So that's it for today. If there are any questions, feel free to reach out to any of us on Discord or next week's Zoom meeting, which you can ask any questions. Thank you for coming to our lesson.
All right.
And that'll be it.
Yeah. So, all right. Bye, guys. I'm going to end the meeting now. If you guys missed anything or want to remember
Wait,
something.
sorry, Matthew.
what's
Star's
up?
asking if we want to stay for DP.
No, that's not us. That's just the execs.
Oh, okay.
Yeah, so if you guys, I'm going to end the meeting now. So, see you guys. See you next
Thank
week.
you. See
Thank
ya.
you. Bye.
Bye.
Thank you for coming.